Okay, in problem number 5, we're asked to graph y equal 1/2 tangent x, and we could label this the way we labeled some of our other functions. I could say this is y equal a tangent bx minus c. Okay, so the a up front, again, is our amplitude, and so we can see that our a is 1/2. And that's going to mean something different here than it did with the cosine and sine function. Now on this one, you can notice, we'll talk about the asymptotes in a minute, but if you notice, this is just the graph of tangent x, and it's climbing basically half as fast if you want to think about it. That could be one way to think about it. Tangent x, if you remember, has asymptotes, and so I'm going to draw them in red, and these aren't affected by this amplitude switch change here. The asymptotes are at pi halves and at negative pi, if we're just looking at one cycle of the negative pi halves. So if you look at the period here is pi. It's different. Cosine and sine have a period of 2 pi, but tangent has a period of pi. You can put in any number you want, except the only things that are going to give you trouble are things that fall on the asymptotes, and those are given, at x equal pi over pi halves plus n times pi, because every pi, if you pick an asymptote and you go pi units away from it, you're going to have another asymptote, whether you start here or here. That n just means any real number, and you can do any x you want to except for those. But anyway, that's because your vertical asymptotes are falling right here. Okay. Usually, if you could kind of find some values. Some of the good values to pick are like 45 degrees for tangent. That's because tangent 45 degrees is 1, and it's because if you remember, if you got a 45, 45, 90, opposite square root of 2 over 2, this is square root of 2 over 2, and this would have been 1. And so when you put opposite over adjacent, you get square root of 2 over 2, square root of 2 over 2, which would be 1. So some important things, unless you've got it shifted or anything to graph on tangent, are the 45 degrees, which I guess would be pi over 4 if you think about it. I'll just put pi over 4, negative pi over 4 here. I'll try to label it. Now normally, if I were to put 1 here and negative 1 here, I would have had a point at pi over 4, 1, and pi over 4, negative 1. The shape of our tangent graph looks like this, okay? And we would have had a 0 at 0. Okay, so tangent of 0 is 0. I can get that even by thinking about my unit circle. And you have the point 1, 0. And remember, y over x would be the tangent. So 0 over 1 would be 0. You can use these points to kind of help you, except they're not nearly so helpful on tangent because it has so many undefined places. It has asymptotes every pi unit. So 0 and 180 degrees are your best bets there because of where your asymptotes are to actually get some values. Now, how does the amplitude affect this? It's not like cosine and sine. Normally, if I at 45 degrees or pi over 4, I was at 1. Well, now it's climbing half as fast. That amplitude out front affects how fast this thing climbs. So let me graph in green. Normally, it would have been pi over 4 is 1, but because it's has an amplitude of 1/2, this point's actually 1/2 here. So you could kind of do some of what you did with, if you just want to graph your 45 degree increments on this one. Man, my mouth today, I'm not saying the right words. I could just say, instead of 1 and negative 1, I could put 1/2 and negative 1/2, and then just show there's points here, and then the graph just approaches the asymptotes, comes through the 0, and comes down like that. Cotangent looks just like this, except it's flipped. I guess you could say it's reflected across the y-axis. Instead of looking like this, cotangent starts on the other side and comes down. Okay, again, we could label this. There's another example, so we'll look at something like this. This is like a tan bx minus c. This one doesn't have any shifts, and again, it's always easier when you don't have the shifts. My amplitude is 2, which means this is going to climb faster because it's whatever my tangent value is, it gets doubled if you think about it. So this is going to climb faster. It's reflected. So this is going to look more like a cotangent graph when I get done with it because of that negative out front is going to reflect it and make it, so we'll kind of notice that. And then normally tangent has a period of pi. And if you think about it, normally it's between, pi halves and is one asymptote and negative pi halves is another asymptote. But this period, so instead of being 2 pi over b, it would be pi over b, and here the b is 2. This means my period is going to be every pi halves, which means that I'll have 2 periods every time I would have had 1, if you think about it. Every 90 degrees I'm going to have a cycle of this graph. So, if we want to graph this, the book gives some suggestions, and let's see if this helps us at all. I've never done it this way, but I mentioned this in class the other day that you could. If you want to find your equations, if you take these little bx minus c here, this part right here, and because my normal asymptotes are at pi halves and minus pi halves, if I were to say 2x, set that whole thing equal to pi halves, because that's where normally one asymptote would be, and then you set the thing equal to the other asymptote, this will tell you your new endpoints, which that's probably going to be pretty helpful here. With cosine and sine, sometimes I don't know that it's necessary. You can usually do that a little easier. These get to me a little bit more tricky. If I could divide both sides by 2 to solve for x, that'd be the same thing as multiplying by a half. So that would mean that one of my asymptotes is going to be on pi over 4. And if I do the same thing over here, I'll just use a different color since that's getting kind of squished together. If on the second equation I multiply everything by a half, I'll have another asymptote at negative pi over 4. So that means if this is pi over 4 and this is negative pi over 4, those are going to be where my asymptotes are. Let me put those in, and I'll do those in red like I did the previous one. Okay. Now, so that means every, let's see, pi halves. So if I'm at pi over 4, and I think about it, that would be 90 degrees, or pi halves. This would be 3 pi over 2, which is like 270 degrees. I would have another asymptote coming through here. Okay, so I could show 2 full cycles of this graph very easily here. Now, normally, let's say I'm going to graph this little bits at a time. I'm going to graph in green next. The normal amplitude, and let's see, let's kind of get some values going here. You know that there's a 0 in the middle of each of these, so I could go ahead and put that in. There is kind of something that can help me ground my graphs right here. I know that they're going to go through 0, 0, 0. They're cycling faster, and so if I want to divide those into 4 parts there, normally at whatever this thing over here would be pi over 8, this point between 0 and pi fourths, that would be pi over 8. On a normal trig graph, that would go up to 1 and negative 1, because 2 times pi over 8 would be the pi over 4. Will give me the 1 value here. So the thing about this is it has an amplitude of 2. So it would actually go to 2 and negative 2 for those values. So it would be like this and then like this. But then I have that reflection. So let me graph in, let me pick maybe orange now. If I reflect across the x-axis, this is going to put this one over here. The 0 one stays the same, but this green dot's going to go over here. So I could graph like this. Could do this. Let me divide that into 4 parts. I can kind of see the pattern now here at 2. It's going to come through. And down here at negative 2, hit a point. Now the orange graph is actually my final graph. So I had to change the period. And I did take advantage of this fact here that bx minus c was normally the endpoints are pi halves and negative pi halves. So I'll put plus or minus pi halves here. I did use that to help me kind of to find where my new asymptotes are going to be. So it's pretty helpful here for tangent. And this graph is done now because it's reflected. We took the amplitude into effect, and we changed the period on it.